Hello students, welcome to this particular lecture. In this particular module, we will look into the approximate multipliers. So it's basically a multiplier circuit, and then we will try to understand how the multiplier blocks are designed, and then try to go about approximating the multipliers. There are certain advantages of using the approximate multipliers, especially for today's image processing and signal processing applications. And we will have a look at one such image processing application. Uh, so most part of this particular, the lecture is actually taken from this particular reference paper called as Approximate Multipliers based on the new approximate compressors. And the approximate multipliers, we'll go through in achieving the approximate multipliers. We'll have to understand compressors, and we will also try to understand what does the approximate compressors mean. All right, so moving ahead. So approximate, multipliers comes under this broad domain of approximate computing, right? So it could be an approximate computing, as such, will involve multiplication or the multiplication and addition. It could also involve a division. There are several approximate arithmetic operations that has been useful now in this particular, in today's applications. So in that sense, it falls into the approximate computing domain. Now, what is it? It is a computation technique that returns possibly an inaccurate results. Expecting an accurate results. Instead of that, we are expecting an inaccurate results. And it helps in to reduce the area, delay, and the power consumption that will be involved in the circuit design, and which goes into the application on the chip or a system application on the chip design. Now, where it can be used, it is heavily used in most of the error-resilient applications, where even if you have some kind of an error, it doesn't really matter that much. Some of those applications are really the digital signal processing, and then the image, and then the audio and video processing. Some of them are also useful in the wireless communication. So in that sense, it actually connects the VLSI design to that of the application side. Right, so it is. We will talk about the subsystem design, but then eventually it will be useful for the application side. And this error resilient application represents that where the product, which is an product in the sense whatever is the output of the arithmetic computation, and it's kind of an acceptable outputs, right? So despite some of the underlying computations being inaccurate or incorrect. And the question is, how can we achieve this? One of the old methods is to make it software level approximations. But over the last 4-5 years, there has been a lot of focus on the approximate circuits, and thereby getting the approximate outputs, which we can eventually design in the hardware. All right, so that was a very brief discussion about the approximate computing, and in this particular lecture we will actually talk about the multiplication. So how do we get the approximate multipliers and its circuit design or the block design to be done? So to understand the approximate multiplier, one has to understand what is a multiplication. How do we go about the multiplication in the VLSI domain? So the binary multiplication is one such very standard method, where it is nothing but, you have this, if I consider the 4-bit inputs, 2 of the multiplier and multiplicand, and if I do a multiplication of that, I'll have the partial products, and the partial products can be designed, or it is deduced very, very similar to how our manual multiplication method works. So each of this bit will get, doing an AND operation, we will get this partial products in the first row. The second bit, when it gets, gets ANDed with the A0 to A3, will give us the second row here. Of course, there will be an offset here. And the third one will give us the third row here with 2 offsets here. And then B3, when it gets multiplied with the 4 of the A bits, we will get the fourth row, of course, with the 3 offsets. And if I do an addition of all these things, I'll get the 8 bits here, which will be the product bits, S0 to S7, right? So if I actually look into this particular design in a dot diagram design, it's very interesting to see that we call this particular the ANDed operation of B0 to A0 or B0 to A1 or B0 to A2 or B0 to A3 or B3 to A3, all these are nothing but the partial products. So in a multiplier definition, all these are nothing but the partial products. Each of these dots in this dot diagram represents the partial products. So this, this first level of the dots, however it is arranged, it represents this particular P00 to P33, right? The offset here, or an empty spaces here, represents that it will eventually be filled with 0, and then when it gets added, this dot, which is nothing but a partial product, will get added to 0 here. So it will not have any effect, right? So what we really want is, while we are actually adding it up and then eventually getting the product results, we want to make the first stage, here is the case, this is the partial products that has been generated. And then in the first stage, we have, so we make this kind of an arrangement, right? So the first stage will get reduced to from, this is the first stage. So if I consider this particular level, this particular 3 of this partial products can go up here, because it's anyways the addition here, and this 2 can go, this one can go here. So that's what we'll get here. The first stage, we can say that this represents the same thing here, but it is kind of rearranged to some extent. And once I have a rearranged first stage, then we will apply some half adder or full adder, so that we will get the second stage, which is of the length of 3, the maximum length of 3. So here the maximum length is 4 here. In the sense, maximum length means if I consider any kind of a column here out of the 8 columns here, 1, 2, 3, 4, 5, 6, 7, out of the 7 columns here, if I consider the 4th column, that turns out to be having the maximum height or the maximum length, right? So I'm again trying to reduce this, the length of 4 into 3, by applying some half adders here. So this particular, the enclosure here, which is enclosing the 2 of the bits, is nothing but representing the half adder. This particular enclosure representing the 2 partial products, or the 2 dots here, represents the half adder here. And eventually, if I have the half adder here, then I'll get the 3 bits here, and then 1 bit here, and then the 3 bits here, 3 bits here, 3 bits here. So I'm actually reducing from 4 to 3 bits here, 3 dots here, whatever we can say. And in the second stage, we'll do the further reduction and then get from 3 dots to 2 dots here. And finally, if I have this particular stage with only 2 dots, that means that I need to have some kind of an adder subsystem block, which can actually do an addition of 7 bits and addition of this 7 bits. Right, so I need a 7-bit addition, and then finally I will get this results. Right, so here I have written that it's a final carry propagate adder of 6-bit here, which means that I'm going to apply the addition up till this particular dots or the bits here, leaving this out. So this could be anyways, we can consider it to be directly as the first LSB of the product bits. Right, so that's what we do. So we have this particular partial product. So in an overview, the binary multiplication can be recognized into 3 stages. One is a partial products generation and then kind of rearranging. The second is a partial product reduction, which will be like 4 to 3 to, so from the first stage, the length of 4 can be reduced to a length of 3, and then the length of 3 can be reduced to a length of 2 by applying some half adders or full adder designs. Right, so and then the last one is the carry propagate addition, which we do it in the last stage. Once we get the length to be equal to 2, then we apply the carry propagate addition. We can apply carry skip adder, we can apply carry select adder or increment adder, or whatever we want. We can apply there to finally eventually get the product bits. Right, notice that here this is one single dot. This 2 dots represents the half adder, and then this 3 dots represents the full adder design. Right, so we can actually use the full adder and half adder designs to convert, to reduce, in the second stage we call it as a partial products reduction stage. Right, so what we say that this is the binary multiplication. We can also say that approximation can be introduced in any of these blocks. Right, whether it is the first stage or the second stage or the third stage, or even in fact we can say that during the partial product generation as well. Right, so here is an exact multiplier. Here is this is called as a conventional multiplier, also called as a data multiplier, because it was kind of invented by the author Dada himself. So this is the way the data multiplier works, where you have the the 8-bit multiplication, so giving us a 16-bit output. So if you consider the 8-bit multiplication, these dots are nothing but the partial products that are being generated, and then the boxes which are enclosing the 2 dots represents the half adder. The boxes which are enclosing the 3 dots are the full adders. So we apply, in the data multiplier, it keeps applying the half adder and full adder to bring it to a stage where it is only the length is 2 bits, and then finally apply some the fast adders, and then get the product bits. Right, so in all the stages of partial product reduction, right, from reducing the length here to a length of 6 here, to a length of 4 here, to a length of 3, and then finally 2. So we apply the half adders or the full adders. So the sequence for an 8 cross 8-bit multiplier is like this. The length is 8 here, or the height of this the partial product stack is actually 8. In the next stage it reduces to 6. In the next it reduces to 4, 3, and 2. Similarly, for 16 cross 16-bit multiplication, it actually reduces, starts from 16, reduces to 13, then to 9, 6, 4, 3, and 2. And this, in this particular work, I think the benchmark multiplier is considered to be the data multiplier. Right. So let's take a look. Let's take a quick look at the compressors. What do we mean by compressors? So when we apply this half adder or the full adder into our partial product, so as to reduce the partial product stages, we call it as a compressors. So it is basically compressing from the higher length of the partial product stack into a lower length. Right, so and the very primitive compressors could be a half adder or a full adder here. The full adder, as we know already, 3 inputs generates the sum and carry, and then half adder is nothing but 2 inputs will generate the sum and carry. Right, so it could also be called as 2:1 compressor, the half adder, and 3:2 compressors if we use the full adder. Here is the truth table for the half adder and full adder. Moving ahead, so let's take a look at the 4:2 compressors. Right, what do we mean by an exact 4:2 compressors? It is actually realized by the 2 full adders here. So 4:2 compressors will involve 4 inputs. There will be 1 carry input, and there will be a carry output, and then there will be a carry here, and then a sum here. Right. So if I consider one segment, so let me use the pointer here. So if I have a stack of partial products, if I have 4, and then in the neighboring also if I have 4, then I can use this 4:2 compressors, right? And then it is going to generate the carry out here, C out. It is going to generate the sum here, right? And it may take a carry input, assuming that is the LSB side. So I will say that the C input is 0. So I can say that the C input is 0. I can assume that. And then there will be a carry out, or rather I'll say that carry. This carry out is actually going to the it will fit it into as a carry input to this particular 4:2 compressors. So this will be 4:2 compressors. Now this whatever goes into carry input, this particular output will be the carry input to the next 4:2 or the subsequent 4:2 compressors. This carry out will go in as the carry input in the next stage, stage of the partial product. So when we create the partial product, this carry in will go into to the next stage of the carry input here. Right. So the sum will be anyways be considered as a dot in the next stage, or rather as a partial product in the next stage. Right, hope this is clear. So that's why the 4:2 compressors will have 2 carry outs. So one going into the same stage, the second one going into the next stage. Right, so the 4:2 compressors was actually developed using the 2 full adder circuits. So X4 is the LSB side, X1 is the MSB side, and if you have the 3 MSBs, and then the last LSB is actually going into the second, or rather the the full adder side here, along with the carry input. So whatever is the sum that is being generated here will go into the to the full adder here. Right. Remember that I think what we are doing is we are considering this this particular 4 bits as an input, and then we ultimately want to find out the sum and then the carry out. Right. So it is really not whether x4 is the MSB, LSB, or the MSB. It is nothing but we are doing an addition of x1, we are doing an addition of x2, x3, x4. Right, so we need to add this up. So we will use one full adder for the x1, x2, and x3, and another full adder for this sum, whatever is the sum generated, and then so along with that sum x4, and then we will have the C input, and then create the overall sum and then overall carry. All right. So hope this particular understanding is clear about the exact 4:2 compressor. Similarly, we can have 5:2 compressors where there are 5 inputs, and then there are 2 carry inputs, 2 carry outputs, 1 sum and 1 carry. Right, so this can be done using the 3 full adder circuits. So I will have the first full adder will have 3 inputs, the second full adder will have 3 inputs, third full adder will have 3 inputs. The only thing here is the inputs are nothing but the carry input of the first carry input, and then the second or the third full adder will have the second carry inputs, and it will generate the sum, carry, and C out and C out 1. Right. So if I look into the full adder circuits here, the full adder circuits can be represented as nothing but x1. If I consider the sum here, sum can be represented as an XOR gate x1, x2, and x3 here. Sum 2 can be considered as the S1 XOR with that of x4 with that of C in, and that to 1. And finally, this particular sum here will be considered as again S2 XOR x5 and then XOR with that of C in of 2. So if I consider the sum or the delay associated with this extracting the sum output, it will be 1, 2, 3, 4, 5, 6. So there will be 6 OR gates of delay. So basically, a compressor is nothing but a logic circuit that counts the number of ones in the input, right? Number of ones in the sense x1, x2, x3, x4, and then carry input, carry input 1 and carry input 2. Right, so if I have this particular, the partial products which are being generated, now the question is why, can I not apply the 5:2 compressors, 3:2 compressors, 5:2 compressors here, and then make a much more reduced partial product stage in the next stage, right? So ultimately, what we want is, if I want to create a sum of this, it is nothing but the summation of this partial product, summation of this partial product, summation of this, this, and this. So it is a the partial product summation starting from 0 to j minus 1 in the jth column. So the compressors are XOR rich circuits, and partial products reduction is a critical multiplier. XOR gates tend to contribute to the higher area and delay. So if I have some kind of an approximate compressors, then it will be highly beneficial in actually leveraging to that of the footprint, the delay, and then the power, and we can greatly reduce we can greatly get benefited in terms of all these 3 parameters. And of course, we will achieve the inaccurate results, but for some of the applications, it may not have that much of an impact. Right, so approximation. So approximation, how is the approximation done? So the proposed design in this particular paper is nothing but you can represent the partial products in the form of an AND and OR gates, and not use the XOR gates at all. And so instead of an XOR gate which will give you an accurate sum, right, instead of an XOR gate, why not use some kind of an AND gate or an OR gate, right? And of course we will get some error, but if that error will not have that much of an impact, then we will get reduced delay. We will also get we'll also avoid the XOR gate which occupies more of an area, and instead use that of an AND or an OR gates. So to approximate the half adder, right? So let's say the sum is x1 and x2. So if I consider the half adder, it is only 2 bits, 2 input bits, 1 carry and 1 sum. So the XOR gate of the sum is replaced, if I replace that XOR gate of the sum, so the accurate sum of an half adder is nothing but an XOR gate here. But instead of an XOR gate, if I do an OR gate here, and carry is retaining the same, it's an AND gate, so we will retain the same. Instead of the XOR here, we will do an OR gate here. Turns out that in the truth table only one error is likely to be appearing. So this is the output here. The carry is 1, sum is 0 here for 1 and 1, for the inputs to be 1 and 1. Here in the approximate output, I'll get a 1 here and then 1 here, right? So I will have a problem only in this particular case. Right, it is supposed to be 0, but we are getting a value of 1 here. So the absolute difference out of the 4 cases is only one case. So what we can do is the sum is equal to an summation of x1 and x2. I can also consider it to be x1 and x2, comma x1 or x2. Right. So so this results in one error in the sum computation. All right, so what we are saying is, if I consider x1 plus x2, addition of x1 and x2, so what I can say that we can actually do an x1 x2 and then do an addition with x1 or x2. All right, x1 or x2 is likely to give us one error here in the sum computation. Alright, so if I proceed further, now why not use this AND and OR recoding for our different size of compressors? So what here I have written is in our partial product generation. So this is my 8-bit X input and 8-bit Y input. If it gets multiplied, I'll get the partial products. The partial products would be of 16. The length here will be of 8 and 8 bits. Will make it 16 bits. The height here, the largest height will be nothing but the 8 bits, right? So here what I've done is, I've represented in different colors just to ensure that, finally this particular representation will make it to an OR gate, and then the other color will be represented as an AND gate. So what we really need is, x1 and yj, xi and yj of the I plus jth column, right? So if I consider I plus jth column to be somewhere around this, right, so it will be nothing but I plus jth column will represent xi dot yj, and it will also represent xj and yi, the dot product of the partial products of xi, yj, and then it will also present xj, yi. If I consider the I plus jth column in the partial product. All right. So if I actually consider those two things, so what it really means is if I consider x7 y2, right, in one of these columns, and x2 y7. So if I pick these two partial products, and if I want the sum, basically we want to add all of them, right? So why not add these two together, right? So if I want to add these two together, right, the addition, what we can say is the addition of this can also be represented as an ANDing of x of this particular partial product. So I can say that this is the partial product ij, and then this is the partial product ji. Right? I can actually do an ANDing of pij and pji, and ORing of pij and pji. So this actually the summation of these two partial products can be represented as an AND and OR. So that's why we say that this is an AND and OR recoding, right? So thus in the I plus jth column of the PPM, we can replace a couple of partial products, especially xi yj and xj yi, with a modified partial products of aij and oij, right? So that's what I've done here. So I have represented this one as the OR gate, and then this one as the AND gate. Right. Similarly, for all other 4 terms, we will have the OR and then the AND gate. So the same partial products, what we have obtained from the binary multiplication of this 8-bit, two 8-bit numbers, right? It is now represented in the form of an OR gate, the output of an OR gate, and then the output of the AND gate, right? So for the future references, what we will do is, it is nothing but xi yj, which is nothing but the partial product, and if it has to be summed with that of xj yi, it is nothing but the partial product summation, which will be nothing but the AND operation and then the OR operation, and that has to be summed. So the output of the OR and then the output of the AND, that has to be added together. Right, so the proposed approximate compressors, what they have proposed in the paper is, considering the input bits xi and yj that are uniformly distributed. So if I consider the partial products or even the xi, right? So I'll consider x1, I'll consider y2. As an individual bit, it has a probability. It is, if it is uniformly distributed, we say that the probability of x1 to be 1 is 0.5 and probability of y2 being 1 is also 0.5, right? So that's what if we consider that uniformly distributed of this particular bits, and if all these bits, x1 to x8 and similarly y1 to y8 are independent of each other and are uniformly distributed, then we can say that each of these bits x8 to x1 and y8 to y1 will have a probability of being 1 is half. Therefore, the probability of pi is probability of the each partial product, right, will be half multiplied by half. So because it is the probability of xi ANDing with that of the yi, which will be 1 by 4. So similarly, we can see that the probability of pi to be 0 is 3 by 4, and that's what is written in this particular table. Right, xy, yj and pj. So we will have only one here out of the 4 cases. So that's why it is 1 by 4 of the partial product being 1. Right, so ultimately what we want is, if I have the number of inputs as j, so I will have the partial products p0 to pj minus 1. And finally, the number of outputs we want to reduce from one stage, partial product generation stage, to the next stage. We want to have j by 2 length, and then so on.